Hello, thank you very much for having me. Good morning, everyone. I'm going to talk to you about homomorphic mixing networks. It is, I would say, a pretty new concept in the sense that it needs to be formalized in many senses. There's a lot of research that is aiming to combine these two fields, like the mixing networks fields, that is a technique to anonymize some traffic on the internet, and homomorphic encryption, of course. Then, but there's no like a standard path. There's no like a formalization, mathematical formalization of it. And one of the purpose of this talk, and let me actually put the light mode. It looks far better. One of the aims of this workshop is to talk a little bit about this. Invite you again if you want to talk about this. These concepts, but I will be giving you the basis, the framework to start talking about that, right? So the goal of the workshop, basically to reason around how to apply homomorphic encryption to mixnets at an introductory level. So this is not aimed to be like a presentation full of results of theorems, etc., but it will be presenting some mathematical definitions for us to like ask correct questions about security, anonymity, and how we can have a whole mixnet to be like a play field, let's say, for us to compute on traffic, on anonymous traffic. So the goal to have a theoretical basis to ask natural questions more formally. Again, it's about being more mathematical, because at the end of the day, about security, you have to reason in terms of really precise statements, because when you're making a threat model, you have to know exactly what are the limits and what are the goals of the adversary. And that the only way to have that in a really precise manner, that we have a theoretical background to ask questions, is to have these formalizations, right? Then show that there is still a lot of promising work to be done on homomorphic encryption. It's not like when talking about fully homomorphic encryption and current libraries, etc. It's not the whole story. We have a lot of research still going on, and a lot of other cryptographic techniques that needs to be combined with these other homomorphic encryption schemes. And last of, but not least, maybe it is cheesy to say, but maybe have fun. I mean, I don't know how many of you already have some mathematical background or already work on fully homomorphic encryption. But I mean, if you're here, it's probably because you are really interested here, and we are all nerds in some sense, right? So we are having fun. Okay, so what I'm referring here to homomorphic mixing network is in a clear statement, is a mixing network. So of course you have to know what a mixing network is. If you are not sure, it's all right, because I'm going to be introducing the formal terms later, but basically a mixing network is like the Tor protocol, that is that dark web, let's say, that you're bouncing messages in an anonymous way, that you want to send a message from point A to point B, and you can do it by bouncing randomly, right? So it is untraceable. So a mixing network, but that allows transforming data on traffic in a secure way. So of course, here we need to be clear of what exactly do I mean when I say securely? Like, what is to transform securely? Securely can mean private, that it preserves the privacy of the mixing. Maybe that it is resistant to some specific attack. We have to formalize that, of course. Then what exactly does it mean for me to transform the data? Like what kind of operation do I want to do on the mixnet? And why do I care? Or what transformations are even possible, right? We're going to actually see that they're not, the whole family of transformation is not actually possible, because there are some security issues that comes up if we ask too much for this framework. So I'm going to be introducing in a simplified way. Of course, still it is mathematical, and I'm going to be like really quick about it, so you can ask questions later, or we can talk on the whole if you want. But the thing is that I'm going to be introducing some concepts that maybe you already know, but it's for us to be in the same page. So first, an encryption scheme. It is a triple of algorithms, specifically probabilistic polynomial time algorithms. Don't worry if you don't know exactly what that means, but basically, the first algorithms is like a little machine that outputs a pair of keys. We have here the PK and SKs are the public and secret keys spaces. So these spaces are usually finite fields, or maybe some algebraic structure that is comprised of several like fields or rings, right? It can get even more complex. You know that you can use algebraic curves, etc. And it depends on your scheme. So I would be just saying that these are spaces, algebraic with some algebraic structure. Then we have the encryption function that takes a secret key, takes a message, and I'm going to be getting a ciphertext, right? So here I'm saying the M and the C are respectively the message space, cipher space. These two also have some properties, and the thing is that when we are starting to formalize this, we have to think about what are the properties of these spaces. It turns out that if you want to have fully homomorphic encryption, or any kind actually of homomorphic encryption inside Mixnets, since as we will be looking at later, you have to compose the encryption functions. So you have you require that the domain, the codomain of the functions are the same. So these M and C must be the same in our case, but in general they're going to be different, right? And finally, we have the decryption algorithm. Then this is the condition that it is actually an encryption scheme. So basically, if I want to decrypt something, I need a secret key, and I need the ciphertext. And I'll be getting some message back, but I'll be really sad if that message is not the message that I originally came up with, right? So basically, if I do an encryption with that message M, and I decrypt it, I should be able to receive back the message, right? The original message. But of course, it turns out that not every encryption scheme can do that, and actually the most interesting ones and the most useful ones do not do that all the time, but at least they can guarantee that in some probability distribution that depends on the cipher and message space, they're going to at least be greater than some error bound that is really small in some security parameter n, right? So we have this is only for us to be in the same page, because now I want to talk about what exactly in some precise terms is homomorphic encryption. This is needed for us to formalize the what exactly is that the Mixnet require us to be homomorphic with respect with, right? So in this case, this is a more general sense of homomorphic encryption. It is not fully homomorphic encryption, but only with respect to some specific function. So let's say we have this function f. In this case, we are transforming some ciphertext into another ciphertext. Of course, we want to compute over encrypted data. And we have this encryption scheme, and we say that encryption scheme is going to be f homomorphic if we have this property in this equation. So basically, you can either compute over the message or compute after encrypting, and it should have the same effect, right? So basically, whenever you have the encrypted data, you compute over it, it's as if the F actually came in here, right? And is only operating on the message part. So here, of course, if you notice, this is only possible if M is equal to C, because this domain needs to be the ciphertext, but in this case, we're taking a message, so this must be the message space. So in this case, is the same. So just a clarification here, we're going to be sometimes writing this up as if this PK, the public key which we are encrypting, is like a property of the function itself, and we're just giving one argument here. Okay, so the thing is that what kind of functions do we really care about? There is a whole class of functions that fully homomorphic encryption is needs to work on, that is called Boolean functions. So the Boolean functions are basically all the functions that comes from this space, that is the space of k bits. So basically you either have a 0 or a 1, and you have k copies of it, so maybe 0011 or 11010, etc. And you return only one of them, right? And more generally, we have this thing called Boolean circuit, that is basically you take a lot of these functions and you relate them in some graph. So I'm going to be giving an example. But basically, you either, on each of the vertices, you are going to have either a Boolean function that is called a member of the basis. So basically, you're not going to consider every Boolean function, but only a subset, and those are going to be called your basis. And from that basis, you can have some inputs, and through that graph, you're going to recover some output. So just to give a quick example, well, before it, this is the note about what truly fully homomorphic encryption is. So I don't know if you have seen before this definition, but basically what we really call fully homomorphic encryption is when it is C homomorphic in the sense of the previous definition, right? So it was F homomorphic if we have that condition of equality between the F function and the encryption algorithm, right? But in this case, it must be with respect to this C. So DC is, remember, the Boolean circuit. Basically, the Boolean circuit, since it is a set of all these functions, you're going to be thinking about a function that takes a lot of inputs and potentially returns a lot of other inputs, right? But it is still a function. So if you have this commutativity property between the encryption scheme and the circuit, then it is fully homomorphic. Since it is for any Boolean circuit. So just to be clear, this is an example of the of what a Boolean circuit is. So if you come here down there, it is we have some inputs, x1, x2, and x3. In this case, we have to follow the arrows, and we see that first we have this symbol that is the AND symbol. We had AND and NOT and OR, and since we only have these three functions, that is AND, OR, and NOT, these are the bases. So we have a basis of three functions, and we have these three inputs, and we just process according to their truth tables, and we have an output. The thing here is that this is just a curious fact that these are enough in the sense that these three functions are they generate any other Boolean function that you want. So if you are homomorphic with respect to this Boolean circuit with this basis, then you are fully homomorphic in that sense. So okay, I'm going to go through the mixing example definition and then example. I would like to say that. Okay, no, it's all right. So. Here, mixing network. So a mixnet, like I said before, it is like a Tor protocol. You have a lot of nodes, and those nodes are, they all have a private key, this secret key, and a public key. And it's a public key infrastructure, basically, in which you can encrypt any message to any other of the members of the network. But the thing is that we have a global encryption scheme with which we are going to be preparing some messages in the following way. So basically, if we come here, sending a message through the Mixnet means exactly to prepare this object that we call the onion layer cipher. That is basically, if you have a message M, so this little message here, we are going to encrypt it with one specific private public key. So we start like this. So this PKN is a member of a subset of nodes. So imagine that maybe you have 1,000 nodes. But for one specific path, if I want to send one message to another server, and I don't want it to be traceable, then I'm going to choose a subset of those nodes, maybe only 100, and those hundreds are going to be, these ones are numbered here for 1, 2, up to n, right? So I'm going to be encrypting with the last one, then that is going to be returning me another ciphertext, and then I'm going to be encrypting that one again. And in that sense, all over until I get to the first one. So this is what we call an onion layer message. And exactly this is what we are going to be trying to make into a homomorphic sense, right? So maybe you are already anticipating some like difficulty here, because if we want this to be homomorphic, you are going to need to commute. Like, for example, if I want to have a little f here, then I'm going to need that f to enter every single one of these, and to basically commute with all of the other encryption functions. So that is all right. That's actually one of the first difficulty that we have. So the thing is this one, the property that we actually desire, what we were talking in the beginning, that if we want to have computation, arbitrary computation on encrypted data during the traffic of the mixing, you need the mixnet to be able to transform data with some f. Let's say the f is being fixed in this case. F, it can be, well, with the properties of f, we're going to be looking at them later, but basically with that f, we want that during traffic, we're asking that set of functions for every possible j, sorry, to be f homomorphic, specifically this, right? And the thing is that this should happen for every possible mix path, and that is the actually hard part, because if you choose a specific mix path, maybe it just happens to be the case that we have these, maybe these are 100, again, 100 functions, and you got lucky, and then you actually can like commute this f with all of this. But if you have a general permissionless network in which members can just enter and exit your network at any time, then it is really, really hard to just assume some properties of the network nodes such that this always fulfills. So this is actually the most hard part. And here we're going to talk a little bit about the allowable functions. That, since we talked before, it is not as easy as just saying, well, I want to do machine learning over the mixing traffic, right? We know that in fully homomorphic context, we can use fully homomorphic encryption because most of machine learning is just additions and divisions and some inverses, and it just reduces to some, how do you implement that in GPUs, right? But in this case, if we are through the Mixnet, we have to, again, be homomorphic with respect to every of encryption functions. So the allowable functions need to get note of this. So it is actually possible to show that requiring such a strong condition for all the possible paths is too much of a constraint, and it will make the encryption scheme vulnerable. This is actually what we call the malleability of the encryption scheme. So malleability is basically when you have some capacity of some structure that you can recover from the message space in the cipher space. So you don't want some structure to have in the, like, for example, if the message space are some transactions and you know that transactions are related in some ways, for example, 2 transactions come from the same person, you don't want that correlation of transactions to also be retrievable on the cipher space, right? So that is basically this condition here, that it is too strong of a condition, it becomes too malleable. And to solve this, what we are implementing in security labs is 3 approaches, basically. The first one is to re-strategize how to select the path. So since the problem is that you cannot make it for every path, then you can like make something that we call ephemeral path. So basically, on some specific instances, you can design the path and redesign it on the spot if you don't have the desired properties, right? So this is the first way of solving it. The second way is to limit the kind of transformation and use randomizable encryption. So what this means is that we don't actually want to do machine learning on mixed nets, right? Only some specific use cases, and in our specific use case, we only want to authenticate. So authentication is a specific class of functions that is actually pretty simple in terms of the whole Booleans, the space of all Boolean circuits. So that is far more easy. And what we mean with randomized encryption is basically when we get a ciphertext, and we can transform the ciphertext without losing the structure of how to get back to the same message. So basically, one message can have multiple ciphertexts, and we can like move freely across all the possible ciphertexts that are related to that same message. So there's some malleability there, but not too much, because we are limiting the kind of transformation that we use. And finally, the other approach, and of course the real approach, is to have a more sophisticated, the real approach is to have a combination of the three strategies, but the last one is to have a more sophisticated encryption scheme also. That is something that requires, of course, that the whole industry push forward into this, and that's why I'm inviting you all into discussing more this topic, right? It's not discussed enough in the sense that we have to still formalize some mathematical background and some theorems and results about this. My own research, and you can look into our white paper. I can share it to you later if you want. We have some results, but of course this is only possible if we join forces and research together into this. And with that, basically, thank you very much for the space, and now we're leaving you with some quotes that I really like.
All right. Well, thank you very much.